Alexander McAddy, official earthquake forecaster for the U.S. Weather Bureau, had a nighttime routine.
For 20 years, I have recorded every earthquake I have felt. I kept a daily log of Earth movements. My custom was to sleep with my watch and spectacles at bedside, notebook open to the date, and pencil ready. These were laid out in regular order. My record of 1906 April came in a frenzy. The first shaking was incredibly strong, lasting over 40 seconds. A strong aftershock hit 8 minutes later. Another aftershock at 5:25 in Bedlam rain. More shaking at 5:42. And then the fires began.
Get out of there.
The Temblor of April 18, 1906 came out of the sea just offshore from San Francisco. Moving northwest and southeast at more than 7,000 miles an hour, it had an explosive power equal to more than 7 million tons of TNT. In this great violent movement of the earth, tremors unleashed almost unimaginable devastation. Streets buckled and humped into undulating waves and split open into deep gashes. Buildings, wood and concrete and glass collapsed, shattered, crushed, twisted, tangled and crumpled so that sidewalks were impassable. Gas lines and water mains ruptured, sewer pipes smashed, electricity gone, trains and trolleys stopped, no post or telegram. People died pinned beneath the wrecks of buildings, and the tremors wouldn't stop. On April 18th, there were 135 aftershocks. The fires that followed were even more destructive. Without water, fire could not be stopped. For 3 days, San Francisco was a blazing inferno. People think of April 18, 1906 as the Great San Francisco Earthquake and Fire, but it really was a Northern California quake, ripping apart the earth over a distance of nearly 300 miles. It was felt as far north as Coos Bay, Oregon, as far south as Los Angeles, as far east as central Nevada, a distance of nearly 200,000 square miles. It was registered on seismographs all around the world, including London, Tokyo, Moscow, and Cape Town, South Africa. Earthquakes are one of the deadliest of all natural disasters and one of the hardest to predict. Volcanoes typically show signs of unrest. Earthquakes strike without warning. How can scientists learn to predict the precise time, place, and magnitude of an impending earthquake? In the 100 years since the Great Northern California quake, science has made astounding progress in understanding how to answer those questions. In 1906, little was known or understood about earthquakes. In fact, scientists didn't even know how they occurred. The earliest records of California earthquakes were made by padres running the missions. The Catholic missions ran south to north in California. Their adobe brick construction often crumbled due to earthquake shaking. Upkeep and maintenance of the isolated missions depended in part on careful record keeping to ensure a reliable flow of supplies and support from the Vatican in Rome.
Following on that, we really didn't have a lot of information until the time of the gold rush, when many more people came to the area. Newspapers rose up all around, and they recorded many earthquakes and kept careful accounts. And that was sort of what seismic record keeping was until about the end of the century. In 1887, the first seismometers were actually brought to the Bay Area, very early models, and they were brought here by astronomers from Lick Observatory who were concerned about how all these Earth movements were affecting their astronomical observations. In the 1906 earthquake, the seismometers around the Bay Area went off scale, except for the one at the Lick Observatory, and that's actually our first strong motion, that is strong shaking record of an earthquake. The first real records of earthquakes were actually kept by people interested in earthquakes, and one of those, and probably the best, was Alexander McCady. He was with the U.S. Weather Bureau. He'd been interested in earthquakes. He came to this area and started noting when they occurred and what their effects were.
What followed the April 1906 quake was really the beginning of earthquake science in the United States.
Each person is going to be responsible for reporting on their own region and getting this data together so we can figure out exactly what happened here.
3 days after the earthquake, with the city of San Francisco in ruin and damage and destruction all across Northern California, the governor ordered the formation of an earthquake investigation commission to look into the scientific origins of the earthquake, the destruction it caused, and to come up with some answers.
The scientists realized they had never seen anything like this before and were inspired to comprehensively study the quake. They realized they needed to gather every shred of information, every remote piece of data.
Many of the important things that they collected were the things that one can see just by directly walking out and looking at the fault or looking at structures that were damaged. What was the nature of the movement of the fault? How much did the fault move? What are the consequences of the shaking of the ground in places of different soil types?
More than 20 scientists contributed. They studied every seismic report from around the world. They interviewed eyewitnesses. They recorded every visible crack in the earth and every destroyed building. They even looked at 8 years of tide gauge records prior to the earthquake and 1 year after. And they discovered and walked every inch of the San Andreas Fault, from southern to northern California, about 700 miles.
That commission was chaired by Andrew Lawson, famous geologist at UC Berkeley, and they produced a monumental report on the earthquake.
The report of the California Earthquake Investigation Commission is referred to informally as the Lawson Report.
The report came out in 1908 and is still in use today. It's one of the most important scientific compendiums of an earthquake and provides a rich basis for earthquake research even today.
Modern technology has given today's scientists the opportunity to reinterpret the Lawson Report and find out more about what actually happened in 1906. Information they unearth can help forecast inevitable California quakes and help save lives when they occur.
A violent shaking.
My bed was going up and down.
Cobblestones danced like
Buildings crumbled.
Flat.
Not a soul
The first
escaped.
shock
Tangled
knocked over
wires,
the furniture.
warped metal girders,
Terrific
remnants of
trembling.
tottering
There were
furniture
heaps of
bumping
bricks and
around.
Hung onto the
stone.
sides of the wall while the building seemed to split.
There was heavy damage as far away as 60 miles from the fault. Why was damage from shaking greater farther away from the rift? And what can scientists learn from that?
The attention to detail in the Lawson Report of all the geological features related to the earthquake was matched by an attention to detail of the effects of the earthquake, that is the shaking intensity. There are more reports of damage and shaking intensity in that report than we have for any other earthquake, even today.
Shaking was one of the most obvious things for the scientists to analyze immediately after the earthquake. You could see it. You could easily record all the damage.
The commission members collected all kinds of personal reports, gathered reports from newspapers, and what they found is, in general, as you might expect, the shaking decreased as you went with distance from the fault. But what they found locally, the shaking intensity most depended on what was right underground. The shaking was lowest on hard rock and greatest on soft material, and in particular, the highest shaking intensities we found on bay fill, that is made land created by filling in the bay, often very poorly consolidated. Another good example of that is the town of Santa Rosa that sits well off the fault. It had actually the greatest intensity of shaking per square area of any town, and that was in part because it sits on a large basin of soft material and may actually be related to things going on the fault.
Research in shaking over the years has led to shake maps. Today, seismographs record the shaking at over 1,000 sites in California. High-performance computers and advanced instrumentation have given scientists the capability to analyze data in a whole new way. Shake maps depict where shaking will be most likely when an earthquake occurs at a specific location. They show how strong the shaking will be, which is critical information for designing buildings and structures that will resist shaking. Real-time shake maps are available for all of California. When an earthquake occurs, shake maps are accessible online on the World Wide Web to help save lives.
In 1906, the San Andreas Fault ruptured to the ground surface, and scientists were able to go out and map it along the entire length of the rupture, which went from near San Juan Bautista for almost 435 kilometers all the way up to Shelter Cove. Up until recently, aerial photographs like this were the best technology that we had for making maps of the fault. And you can see in this area, we have a very dense redwood forest cover over the fault, and it's very difficult to see very clearly where the fault is. We now have a new technology called LIDAR, that stands for Light Detection and Ranging, and it involves an airborne mounted laser that sends energy down and allows us to create an image of the ground surface. We actually get two images from LIDAR. We get the image of the canopy top, which is shown here, very similar really to the aerial photograph. But what's great about the LIDAR is that you can create an image of the ground surface underneath the trees, so that using the computer you can actually strip away this forest cover and you can see what's actually there beneath the trees, and you can see the San Andreas Fault very, very clearly. Right now we are standing right there. We can use these images to help us pinpoint likely locations of good trench sites where we can do detailed studies that allow us to determine the timing of prehistoric earthquakes, that allow us to determine how fast the fault has been moving through geologic time.
Paleoseismology is the study of earthquakes before instrumentation.
Well, one of the things we do to study active faults is to put trenches across them. And these trenches basically they're books for reading the past. The top of the trench is the present day ground surface. We look down through the trench, we see different layers. Each layer represents a period of time, and we can really read the Earth's history going back in time.
This is the longest record of earthquakes on the northern San Andreas Fault that's ever been studied. What we have is 10 earthquakes over the last about 2,500 years. At the time of the earthquake, the ground ruptures to the ground surface and it forms like a fissure that fills in with material. The fissure then fills up with material on top of it in a flat-lying way. And by looking at the fissures here, here's a big fissure, and it was capped by the sediment on top of it. So we're able to date the fissure fill and the sediment on top of it to bracket the age of the earthquake.
The idea is to build up an inventory of the times of past earthquakes to see if there's a pattern, to see what kind of variability there is, and to use this information in helping us to forecast when the next one's going to happen.
Recent earthquake forecasts have been based on data from trenches like these across a number of Bay Area faults. How have science and engineering helped to improve emergency response since 1906? Stay tuned for this incredible story.
People all seemed to be in a daze.
Everything was confusion.
Hospital floor fell through.
Hopelessly little help came.
All the water mains were broken.
Firehouse and police station.
No post, no
The streets in the
telegrams.
neighborhoods were fast filling with refugees.
Another clearly visible thing scientists studied after the 1906 earthquake was the emergency response. It's estimated that there were over 3,000 direct and indirect deaths after the quake. How many more lives could have been saved by better emergency response? Well, science is helping with valuable new tools, like the California Integrated Seismic Network and its CISN display. Here's how it works.
We have a very dense seismic network that has been jointly funded by California and the USGS. That provides us data within seconds to minutes for large earthquakes in southern to northern California. We've partnered in developing ShakeMap, which is this display of real ground motion. So we're not just talking about epicenter and size any longer. We're talking about what the ground is actually doing under buildings, under our communities.
The way I like to think about it is if you were standing over a puddle and you dropped a stone in it, you would watch the water waves go out, and those water waves are analogous to an earthquake. The earthquake generates sound waves, the stone dropping in the puddle generates water waves. It's all the same phenomena. And we have little sensors in the puddle or seismic stations on the earth watching that sound wave go past, and we pick that up instantaneously with our seismometers. That signal is sent here within seconds. We have computers that are analyzing that signal, and if they see there's an earthquake, they report it. We locate the earthquake, determine the location in terms of latitude and longitude, the magnitude. That sets off a whole chain of activities, one of which is the ShakeMap.
Shake maps and other details on specific quakes are delivered within minutes on CISN display. This rapid delivery is crucial for response, for saving lives, and for inspecting everything from roads to bridges, buildings, and more.
Well, one of the things that we've done in California is that we've provided essentially real-time views of earthquakes through CISN display, through ShakeMap, down to the emergency managers at the local level. So when an earthquake occurs, they know whether they're at the edge of a very large earthquake or in the middle of a small quake. They know how to respond. We're all having the same picture of the ground motions within 5 or 10 minutes after the earthquake, so that we know whether we have to ramp up a state response or whether we can focus on local mutual aid to deal with the damage.
Knowing something about the ground shaking levels and something about the performance of our bridges and how they respond to certain ground shaking levels, we can make an assessment of which bridges may have been impacted most by the earthquake. We have CISN display running at most of the traffic management centers now, and they'd be the first line response when an earthquake occurs. They'd see that the earthquake occurred, they'd get epicenter magnitude information, they'd get the shake maps as soon as those became available, and they would be the ones that would put our emergency operations centers in motion.
What we have in place right now is a process where we take shake map information and we overlay it into our analysis program. And the analysis program will do analysis of every component in our system and give us a map of the components that are damaged and the impact on system operations. So within a few minutes after future earthquakes, we'll have that information available, and that helps us with our emergency response and what to do with our passengers and trains in our system.
We're prepared to use real-time shake maps here at our studio, and with these maps, news organizations can swiftly provide vital information to millions of viewers immediately after a quake. And the bottom line is that these maps enable the media to provide faster, more accurate information to help save lives.
The Bay Area is particularly vulnerable to the commute issue, where you have people leaving their homes in the East Bay, commuting into the peninsula, and may not be able to get home at the end of the day if there's an earthquake. So we want to be able to get information out as quickly as possible to everyone.
To best coordinate response following a quake, the State Office of Emergency Services has backup power and communication systems built to withstand worst-case earthquake shaking. When an earthquake ruptures the earth at the surface, that's easy to see. But to predict earthquakes, scientists need to learn what's below the surface. What are the underlying processes of the Earth?
The Earthquake Commission found that the San Andreas Fault shifted along this length of more than 200 miles. How is that possible? How could the Earth have shifted suddenly over such a great distance? There had been no earthquake that had been seen like this before, and it was a question that confounded scientists until the development of plate tectonics theory in the 1960s.
Plate tectonics is the overall model of how different parts of the Earth's crust are moving relative to each other. And the crust of the Earth is broken up into major plates. They slide past each other, and they move on faults. The San Andreas Fault is the major fault zone helping slide the North American plate past the Pacific plate. And this movement occurs at about 2.5 inches a year. Doesn't sound like very much, but over geologic time, it builds up into a lot of slip that has to be accommodated.
These great strides in understanding earthquake processes track directly back to the 1908 Lawson Report.
Perhaps one of the most important results that came out of this study was the development of Harry Fielding Reid's theory of elastic rebound. He used the information collected from land surveys that allowed him to measure the changes in land surface that had been caused by the earthquake. This was something that had been understood in rough form before the earthquake, but he developed the first scientific theory about how forces accumulate along faults only to be released in earthquakes. We call this the elastic rebound theory, and it's the foundation, really, of our modern understanding of the earthquake process.
If you can think of the crust as a slab of rubber, and you're grabbing the rubber from the two sides and moving it past each other, if the fault itself were Teflon, the rubber would just move by and never be distorted. But because the fault has friction, then the rubber gets distorted and stresses are built up on that surface. So that process is very, very slow, 1 inch a year, and suddenly, at the time of the earthquake, a very small piece of that high friction surface is going to let go. And as it does so, it starts slipping. And in the space of a few seconds, that slippage speeds up from 1 inch a year to 5,000 miles an hour. And that process then tears down the fault at these high speeds until it comes to a stuck patch where it can hang there for several seconds. If it's going to be a large earthquake, it's going to burst through, speed up again to 5,000 miles an hour, and go flying into the next knot in the piece of wood, if you like, hang there, and then burst through again.
In parts of California, we just really have the San Andreas Fault. It's the major feature. But in places like the Bay Area, the fault splays. It's like the trunk of a tree. It comes into the Bay Area, big branches come out. These are the major faults like the San Gregorio and the San Andreas and the Hayward and Rogers Creek, the Calaveras, the Concord Green Valley. And they accommodate most of the movement. And then even little faults come off of them, and they're like smaller twigs. Each different size fault produces different size earthquakes. And here in the Bay Area, we have many faults of different sizes spread out across the entire region.
Each of those faults could produce a damaging earthquake. In fact, taken together, we think a damaging earthquake is nearly twice as likely to happen as not over the next 30 years.
Earthquake information for the Bay Area, California, and worldwide can be found at quake.usgs.gov. Menu items link to things like Did You Feel It?, shake maps, and the Earthquake Information and Preparedness Handbook, Putting Down Roots. Science now gives us all a way to clearly see and understand the earthquake risk in our own lives.
We looked down to City Hall. You could see
Its
right
great
through it.
Grecian columns had crashed to the ground.
The dome looked like a huge skeleton. The masonry had been shaken away from the steel frames.
When the 1906 earthquake destroyed City Hall, no one knew how to rebuild it to resist future quakes. Even if we learn how to predict earthquakes, we still can't stop them. There will still be damage to our buildings and structures. So how are structural engineers learning to reduce that damage and save lives?
The structural engineers in the Bay Area are developing new techniques and new technology that they're applying in new buildings. Plus, since Northridge and Loma Prieta, they've developed new technology and new techniques and guidelines that are being used nationally for retrofitting existing structures. This building incorporates two new techniques for steel frame buildings, a dog bone joint system and an eccentrically braced framing system, and both of these systems were developed in detail so that the building can absorb and deform without failing, without falling down, without killing people. After Loma Prieta, structural engineers determined that the bridges didn't perform properly, so they came up with a technique to jacket the columns with steel casing. These 10-foot diameter steel casings provide the confinement so that the column has the ductility, strength to deform and make it through a big earthquake without this freeway collapsing and people getting killed. Here we are in Berkeley, California. This is a parking structure. What the structural engineer did to retrofit this building is he put the lateral system on the exterior of the building, and this is a conventional solution where they use a concentrically braced steel frame to protect this building from falling down in a big earthquake.
In the last 20 to 30 years, engineers have made buildings a lot safer. But once structures are built to keep everyone alive, the question is, can engineering save the building? In our region, there are hundreds of thousands of buildings at risk.
One new technique that engineers have developed over, I'd say, the last 10 years, it's called performance-based engineering. And because we have the capability with the technology and understanding the materials, we can tune the buildings to improve the performance. So if you have an owner that wants to have a building that not only survives an earthquake, but it remains functional after an earthquake, we can engineer the building so that you can get back in the building right after the earthquake and continue operations like hospitals, like police stations, like fire stations.
You shake the building from the ground and you can imagine 50 miles in any direction, the whole ground shaking. And anything sitting on top of it will also shake. Now, buildings are not completely rigid. They have some flexibility, so when you shake them at the bottom, they sway back and forth and they kind of wiggle around a little bit. And the more they deform, likely the more damage you have. So if you can prevent the shaking from coming up into the building in the first place, that's one really good way to limit your damage. That's what isolation does. Imagine if you could, if we could somehow float the building up above its foundation and separate it like that. Well, we can't quite do that yet, but what we can do is isolate the building a little bit by inserting between the structure above and the foundation some kind of a flexible system like rubber pads, or in this case, a sliding kind of Teflon-like substance, so that when the ground shakes, the building still shakes, but a lot less than it would if it weren't isolated. So here at the Court of Appeals, there are 256 different isolators separating the structure above from the ground and its foundation.
The Ninth Circuit Court of Appeals in San Francisco is one of the growing number of buildings in the Bay Area protected by base isolation, including city halls in Hayward, San Leandro, Oakland, and San Francisco.
We were very pleased to work on this project. I'm a native San Franciscan. I've enjoyed the building from my birth, and what we really saw was an opportunity to work on a national treasure, one of the very special buildings in the country. It desperately needed seismic strengthening. It was damaged to some degree in the earthquake, and we found out as we analyzed it, it was quite a substantial damage. This rotunda is the major theme for this building. So this entire area was redone, refinished, and it looks just like it did when it was built in 1915. I feel very safe in the building. It has a premium seismic system of base isolation, which couldn't be better than in the world, and I think it will do just fine in any earthquake. So the isolators support the walls support the space frame supports the drum and the dome above, and the whole building is anchored that way. When we look at base isolated buildings, we are very, very pleased with the outcome because we don't see any buildings that have been isolated that have collapsed in an earthquake.
Damping systems, which are really just large pistons, are another engineering approach in retrofits and new buildings that reduce earthquake shaking.
Cutting-edge research on building design to withstand earthquakes is taking place on what are known as shake tables.
Hopelessly little help came. Market Street was
A terrific trembling like a
25 feet deep.
Men were just too
The
far
three
gone.
lower floors were completely crashed.
Buildings crumbled.
Automobiles
Not a
were
soul
doing
escaped.
ambulance duty, carrying the wounded and the dead.
The largest outdoor shake table in North America is at UC San Diego, where they test everything from response to shaking to the impact of a terrorist bombing.
Shake table is an earthquake simulator on which we can build then real structures and then send earthquake ground motions through the table. This particular shake table here is the world's first outdoor shake table, so there's no other facility like this in the world where you can build structures of any size virtually on the table. No height restrictions, no overhead crane capacity limitations to lift big things on the table. And this way we can really test full-scale structural systems. The objective of the building test which we just performed here was to show that we can design concrete high-rise buildings, that they can be designed much more economical than what the current Uniform Building Code allows us to do, namely by using less steel and less concrete in the shear wall. We can actually show that the seismic performance improves rather than getting worse.
So what we have here are the cables that will collect all the data from the sensors, different kinds of sensors. You can see these are displacement sensors that are seeing how the wall breathes, actually moves up, opens up big cracks. These cracks here open about 1/4 of an inch.
The experiment was a great success as the building bent but didn't break, experiencing what engineers describe as just cosmetic impacts from the simulated Northridge quake.
What we are doing also here at the Engelkerk Center at UCSD is a blast simulation. So we use the same power supply that drives this big shake table behind me also to simulate bomb blasts on full-scale structural components like building columns, walls, floors, bridge columns, bridge tower sections, and so on. We have 4 velocity generators. These are servo-controlled hydraulic actuators, very similar to the ones that drive the shake table. The only real difference is that here we impart the forces in 1 to 2 milliseconds. The blast load causes shear failures at the end of the columns, and then the shear failure propagates towards the column center. Now, when we take these S-built columns and wrap them, for example, with carbon fibers like you see here, and then we put the same blast load on, which we had put on the columns in the back, you can see here the columns that they're almost perfectly straight after the test. Just the very top of the column failed a little bit.
The work taking place at a network of shake tables at West Coast universities is delivering crucial advances to prepare California and the Bay Area for the next big quake.
The greater San Francisco Bay Area, the 9 Bay Area counties, has done an enormous amount, particularly since the Loma Prieta earthquake in 1989, to become better prepared in terms of emergency response, but more important than that, to actually understand the hazards and then to look at all of our facilities and to tackle the most vulnerable facilities in terms of infrastructure, PG&E's facilities, the bridges, the highways, and the water pipelines and the sewers and everything, and to bring those facilities up to a standard that either they can be rapidly repaired and restored, or they're hardened enough so that they won't experience serious damage.
We're here at a PG&E work site at California and 14th, replacing old cast iron pipe like this here with new generation poly pipe that's going to be threaded through the old pipe under the street. This is part of a 20-year program that PG&E has been doing since 1985 to replace about 2,200 miles of old vulnerable pipes in the San Francisco Bay Area. Residents of the marina may remember us putting in rolls of pipe after the 1989 Loma Prieta earthquake. So now we're doing it all over the Bay Area, and we're about 80% finished with the project.
On a personal level, individuals and families can take important steps to prepare for the disruptive aftermath of a future quake.
Although the tremendous losses from earthquake and the enormous amount of money that's spent on retrofits, those are staggering in terms of their dollar amounts. People can spend a modest amount of money and take steps that will save them thousands of dollars and maybe displacement from their homes in the event of an earthquake. Strapping your gas water heater, making sure there's flexible connections so that doesn't move around and you don't have gas leaks. Some other things are securing the heavy furniture in your home. You can take the time to put bolts in through your bookcases and tie them into the studs in your walls so those don't top over. Taking care of these non-structural items, taking care of these things that are priceless and can't be replaced, like grandma's china and things like that. Those things need to be secured with quake wax. Those are losses that we can easily prevent in a more typical moderate quake. Big heavy TVs like we've got these days, flat panels and big screens, those can do a lot of damage both to property and to people if those fall over on top of you during an actual event.
Materials for securing items in homes or businesses can be purchased at most hardware stores, and pre-made disaster kits are available through the American Red Cross.
Please be ready to take care of your family, and not just a kit, not just a trash can with some water and some food and some expired prescriptions in it, but please think about everything that you're going to need to be able to stand on your own for 72 to 96 hours.
No time to try to find your supplies. When earth shakes, the lights are out, and you don't know where anything is. You think you'll find them. They used to be in that cabinet, but you know, the thing about earthquakes is things get tossed around. So if you want to be able to find the things you need, you have them assembled in a kit. Have the supplies you need where you need them, at home, in the car, in your workplace.
And also not just to have a kit, but to have a plan. How are you going to contact each other when these things happen? If I'm at work in San Francisco and my wife and kids are in the East Bay, how will I find them when the cell phones don't work anymore? You know, the best thing to do is have a phone number outside California that you can all call and leave a message. I'm fine, here's where to find me. These are critical things, and basically you need to take a look at your life and say, if I had no power, no water, no communications, what would I do? And start to answer those questions in a common sense way.
I never expected to come out alive.
Everyone believed their last moment had
I've never
come.
seen anything like it before.
I want to go home, Mama. I want to go home, pleaded the little one. We haven't any home, dear, she replied.
Everyone believed their last moment had come.
A major earthquake is likely to occur here soon. USGS and other scientists conclude there is a high probability of one or more earthquakes of magnitude 6.7 or greater striking the San Francisco Bay region by 2032. What would really save lives is early warning. Can we solve the ultimate mystery? How and where do earthquakes start?
Will it be possible to give a warning before the next great earthquake, such as the one that happened 100 years ago in Northern California? Scientifically, we don't yet have an answer to that question. We've been studying earthquakes from the Earth's surface for 100 years, but we've been blocked from seeing inside the machine that produces earthquakes. Earthquakes occur deep in the Earth, under miles of rock, and to understand what makes a fault, what makes the machine that creates earthquakes, we have to go inside it. That's what we've recently done along the San Andreas Fault near the small town of Parkfield, located about halfway between San Francisco and Los Angeles. Near Parkfield, we've completed the San Andreas Fault Observatory at depth. It's the first scientific drill hole into the heart of a major plate boundary fault.
SAFOD is part of the larger National Science Foundation effort known as the EarthScope Initiative.
This is about understanding what makes the San Andreas Fault Zone tick. Why do earthquakes start? Are they predictable? What causes them to rupture to the surface and sometimes grow into really big earthquakes?
It's a region in which small earthquakes occur at shallow depth, so we can drill into them. And these small earthquakes have a remarkable property. The same earthquake happens on the same part of the fault time and time again. We're drilling into earthquakes that are about the size of a football field. That's the area that ruptures in these small earthquakes, about magnitude 2, and they recur every year or two. So it gives us a wonderful scientific target, a place that we can steer the drill bit along a 2-mile curving path to go right into the heart of the San Andreas, into these zones that produce these remarkable repeating earthquakes.
This is really about understanding how earthquakes work, and by gaining that understanding, being able to better understand the hazard they pose to society and hopefully reduce it.
So it's going to be possible over the 20-year lifetime of the observatory to watch many earthquakes, to watch the forces as they build up, and watch the process that then occurs as the fault goes from being locked to unlocking at a speed of several thousand miles per hour as an earthquake rupture runs along it.
What's kept us from being able to predict earthquakes is a very poor understanding of what's happening directly within fault zones where earthquakes get started. With SAFOD, we have the first ever opportunity to get directly in a fault zone and see what's happening in the hours, days, or even minutes before the next earthquake occurs. By advancing our understanding of the science of what's happening within the heart of the fault zone, we can determine whether earthquake prediction is possible and how we should go about doing it.
The SAFOD project's continuous monitoring of an active fault is a major advance in earthquake science. It's a chance to answer that ultimate question: how to predict when and where an earthquake will occur.
USGS and other groups have come out and said there's a 2/3 chance in 30 years of a major earthquake here in the Bay Area. So that's provided a motivation for people to start improving the buildings and the infrastructure in preparation for that.
Future earthquakes will be larger and closer. And just as a comparison, the 1906 earthquake was equivalent to the energy release of 30 Loma Prieta earthquakes occurring all at the same time.
In the long term, the way that we're going to be prepared for future earthquakes in California is by having structures that will resist their forces.
Alexander McCaddy wrote this in 1906 to the State Earthquake Investigation Committee. The prime object should be to advise wisely, to set forth the truth, and to provide funds for research and investigation, and in every way work for the benefit and welfare of not only our community, but all of mankind, so far as the effects of Earth movement are concerned.
I was not willing to leave San Francisco then. I wanted to stay, to see the new city which would rise out of the ruins. I felt that my place was there. I had something to contribute, even if only in a small measure.
In 1906, it's estimated there were more than 3,000 deaths, 225,000 homeless in San Francisco alone, 28,000 buildings destroyed, more than an $80 million loss from the earthquake alone, and another $320 million loss from the fire, which devastated the downtown behind me. What will happen when the next earthquake occurs?
If we can succeed in understanding the ultimate forces that earthquakes can deliver to the Earth's surface, we'll be able to give very clear guidance to engineers and architects so that they can build structures to resist future earthquakes, to ensure that our critical facilities such as dams and bridges will not be subject to failure in whatever earthquake may someday hit us.
Within the greater Bay Area, there's probably over 100 distinguished earthquake scientists and engineers, and many of those, including myself, live in the proximity of active faults.
We recognize that we reap the riches of a landscape built through repeated earthquakes. This is why we have the San Francisco Bay as a result of these faults. It's why we have the wine country. It's why we have the beautiful climate. If we're going to benefit from it, we also have to prepare for the occasional bad things that these faults fire off at us. And most people and most of the laws and most of the desire on the part of the population is to build to survive earthquakes and to live safely among them.
Quakes are going to happen in California. An earthquake can hit at any time, and it will surely be destructive. But with the amazing advances in engineering and science, and the commitment of the community to prepare and be ready, surely it will be less destructive and lives will be saved.